I stopped the lecture last time by emphasizing some difficulties that we have. The first one is that the plane on which the martensite forms has strange indices, for example 3, 10, 15, and even that is irrational in the sense that 3, 10, 15 is just an approximate representation of the habit plane indices. The real indices cannot be expressed in terms of integers. So why does martensite form on strange habit planes? We also noticed that the orientation relationship is irrational. In other words, the closest packed planes from the two lattices are not exactly parallel. They're approximately parallel. Why is that? And I showed you some images of the shape deformation which happens when austenite transforms to martensite. And when we measure that accurately, that's an invariant plane strain. That means it appears to leave a plane undistorted and unrotated. So what I'm going to do now is to show you that it's actually impossible to transform austenite into ferrite or martensite and leave a plane completely coherent, in other words, an invariant plane. So even though we observe that the shape deformation is an invariant plane strain, it is impossible to transform the crystal structure of austenite into that of martensite by a deformation which leaves a plane completely coherent. Okay? Right, so these are the crystal structures of austenite and ferrite. And just to remind you, this is the ferrite, and it's got an atom at the center of the unit cell, and austenite with atoms also at the centers of the faces of the unit cell. I haven't drawn all the atoms here just to avoid confusion, but this is what we call face-centered cubic or cubic close-packed, because it's a close-packed structure, okay? And body-centered cubic. And we need to know how to deform this into this so that we can achieve the transformation without any diffusion. Okay? So is there some kind of deformation which will change this structure into this? It looks unlikely. They look quite different, but actually this problem was solved back in 1924 by Bain. Now imagine if I take two unit cells of austenite and put them next to each other. So this is just the two unit cells of austenite. Inside that, I can draw another unit cell, still of austenite. We haven't done any deformation at all. This is just a different unit cell representing the structure of austenite. And you can see that it is body-centered tetragonal. So this is still austenite. We can represent a pattern by many different unit cells. The only requirement is that whatever unit cell you choose has to be able to fill space, right? So just to illustrate that in 2 dimensions, if I have a pattern of, so I'm going to try this new toy now. If I have a pattern in which I have a set of points, lattice points, a regular repeating set of points, then the obvious unit cell here would be a square, right? So if I just join this up, oops, it's not quite a square, but if I then stack those squares in 2 dimensions, I will produce the pattern. On the other hand, I could also draw a cell which looks like this. Whoops, this is not working very well. An inclined cell like this, and still repeat the pattern. I'll do it on the board. Okay, it's easier. So we've got a set of points. Yeah, I can draw a square cell. I can even draw an inclined cell, and there's actually an infinite set of cells that I could draw to represent the same pattern. We choose the cell which has the smallest lattice vectors and the angles are 90 degrees just for convenience, because that reflects the symmetry of the pattern better than something like this. Okay? So in the same way, the austenite can be represented as a body-centered tetragonal unit cell. We normally represent it as a cubic cell, but a body-centered tetragonal cell. The point of this is that now it's very easy to see how to change the austenite into ferrite. If I compress the austenite along this axis and uniformly expand along the horizontal axes, then I generate my body-centered cubic cell. So that deformation is called the Bain deformation, compression and uniform expansion in the horizontal plane. So it's a homogeneous deformation which would change the austenite into ferrite, or if I leave some tetragonality, it could also be a body-centered tetragonal cell of martensite. And the deformations required are written here. So this is just a ratio. Along the z-axis, we just have the ratio of the lattice parameters of ferrite and austenite. And along this axis, you can see that we are deforming the 110 direction of the austenite into the 100 direction of ferrite. Okay? So basically, the deformation which changes austenite into ferrite is straightforward. It's a compression and a uniform expansion along the other two axes. It also implies that there is an orientation relationship between the austenite and the martensite, because clearly you can see the z-axes of the two cells are parallel. So I could write the orientation relationship as 001 of gamma being parallel to 001 of alpha, and 1 bar 10 of gamma being parallel to 100 of alpha. Yeah? Exactly parallel. Obviously, we don't observe that orientation relationship, so there's still something missing from the Bain strain. So this is not the orientation relationship which is observed. This is an exact orientation relationship. So note, this is not experimentally observed. But let's persevere with the Bain deformation, because many people have studied different kinds of deformation which transform austenite into martensite other than the Bain strain. And in all cases, you find that this has the lowest amount of strain energy generated. Okay? So it's the smallest deformation which changes austenite into martensite. So there's still something wrong here, that the orientation relationship isn't what we measure experimentally, but let's just carry on and see whether this deformation can produce an invariant plane, and at the very least can it produce an invariant line, because that's the minimum condition for martensitic transformation. Yeah, you remember that from the last lecture, that to get martensitic transformation you must have at least one line undistorted and unrotated. So what I'm going to do is I'm going to represent the austenite as a sphere. Okay? What happens then to the sphere when we apply the Bain strain? What shape will that sphere become? Yeah, have you ever had an M&M candy? Yeah? So if I take my sphere and I compress it like this and uniformly expand it, then it becomes like an M&M, doesn't it? An ellipsoid. Ellipsoid of revolution about the z-axis, right? So I'm going to illustrate that now. This is how we represent the deformation. This is a deformation matrix, and these are the principal deformations, principal strains, because it's the difference in the lattice parameter divided by the original lattice parameter. And this is a compression, and these two are uniform expansions, just expressed in terms of the lattice parameters. Now, I'm not going to use matrix calculations in the lectures that I give you in this course, but you can download a book from my website called Geometry of Crystals if you actually have to do all the calculations. Yeah? everything I'm going to say can be expressed mathematically, rigorously, and allow you to make many predictions. But today I just want you to understand the theory of martensite, not actually do calculations. Okay, so let's represent the austenite as a yellow sphere. This is my austenite, and here I'm plotting the z-axis, and this is the x-axis. So if I compress the austenite, then this becomes this ellipsoid here, and we have expansion along the x-axis, right? And what I want you to notice is with the Bain strain, we have these two lines here, which are actually cones in 3 dimensions, because we also have the y-axis pointing out of the plane of the board, which has expansion along the y-axis. Okay? So OA becomes OA dashed, and OB becomes OB dashed, and they are of equal length. Right? So the length of OA is not changed by the Bain strain. And similarly, the length of OB is not changed by the Bain strain. Right? Is everyone happy with that? Are those invariant lines? Any ideas? Can I call those lines invariant lines because their lengths are unchanged? Yeah. Why is that? Yeah, you're absolutely right. These are not invariant lines. They are simply lines which are undistorted, but they are rotated. Okay? And rotation means that they don't represent coherent lines between the austenite and ferrite. And there is no way I can find even a single line which is undistorted and unrotated by the Bain strain. Okay? So the second problem with the Bain strain is that it does not leave any line invariant. Okay? It does not leave any line invariant. That means, this is the fundamental requirement for martensitic transformation, that we must be able to find one line invariant between the austenite and martensite, and the Bain strain does not do that. So there is something missing from our analysis. Now, supposing that I take my austenite, I apply the Bain strain, and I generate this as my martensite, and then I rotate the martensite with respect to the austenite so that one of these lines comes into exact coincidence. Yeah? Then the combination of a Bain strain and a rigid body rotation gives me an invariant line. Okay? So if I write the Bain strain and a rigid body rotation, that gives me an invariant line strain. Okay, where R is a rigid body rotation. So the Bain strain is only one part of the deformation. The other part is the rotation, which generates this invariant line. But there is no rotation which will give me two invariant lines, because we need two invariant lines to define an invariant plane. This line has gone further out of coincidence by applying the rigid body rotation. So there's still an inconsistency with the shape deformation which we observe, which is an invariant plane strain. Yeah? Everyone okay so far? Now, the combination of the Bain strain and the rigid body rotation is an invariant line strain. And this extra rotation that we have to put in exactly predicts the observed orientation relationship. So the Bain orientation is altered into the experimentally observed orientation relationship by the rotation that is required to generate an invariant plane strain, invariant line strain. Okay? So exactly the rotation by theta, by this angle here, required to convert the Bain strain into a rigid body rotation predicts the experimentally observed irrational orientation relationship. So this predicts the observed irrational orientation relation. So one problem is solved completely. If I give you the lattice parameters of austenite and the lattice parameters of the ferrite, then you can calculate the Bain strain, and you can calculate the rotation required to generate an invariant line, and that gives you the exact orientation relationship between the austenite and ferrite, and it's only a function of the lattice parameters of the two crystals. Okay? Now, it's quite important that you understand that the orientation relationship is only a function of the lattice parameters, because a rigid body rotation doesn't alter anything, any vector. It just alters the direction of the vector, it doesn't alter the magnitudes. And all I have here is the lattice parameters of the two crystals. So, when you alloy steel, the lattice parameter doesn't change very much. So you don't expect the orientation relationship to change very much. Yeah? So you're not going to get very different orientation relationships between austenite and martensite in different steels. That is what this predicts, and that is what you observe. Roughly speaking, the closely packed planes in the two crystals are approximately parallel, and the close packed directions in the two crystals are approximately parallel. So if in the same steel you see slightly different orientations, that cannot be because the martensite is adopting different orientation relationships, because it only depends on the lattice parameters. There must be some other factor that's influencing changes in orientation, and more than likely the austenite does not have a uniform orientation. So if you do EBSD on austenite, you will find gradients of orientation in the austenite. If you have gradients of orientation in the austenite, you will have gradients of orientation in the martensite. But if the composition is uniform and there are no inhomogeneities in the austenite, then you will get the same orientation relationship repeatedly. Okay? So one problem is solved. We can predict the orientation relationship exactly. And that is by ensuring that the combination of Bain strain and a rigid body rotation leaves one line completely coherent between the two crystals. Is everybody okay so far? Yeah, don't hesitate to ask questions if you have. Okay? Right. So just to summarize where we are, we've solved the orientation relationship, and this applies to any material. Yeah? The combination of Bain strain and rigid body rotation will predict the orientation as long as you generate an invariant line. But what we observe as a shape deformation is inconsistent with this, okay? Because the shape deformation appears to leave one plane completely undistorted and unrotated, whereas this only leaves one line undistorted and unrotated. And there is no way, you saw, that we could add any rotations which would generate two invariant lines. And we haven't solved the problem of the strange habit plane either. There's no explanation so far on why, martensite forms on 225 and 259 and 31015 gamma and so forth. So what I'm going to show you next is perhaps one of the most beautiful theories in all of metallurgy. Okay? It solved all these problems in one go, mathematically and with precise predictions. And the important thing is to understand the basis of the theory. Once you understand the basis of the theory, the calculations are easy. Okay, so I'm going to start with a single crystal of austenite of a particular shape, because that makes it easier to explain things. So here I have a crystal of austenite, a single crystal of austenite. And when it transforms to martensite, we get a shape change which is like a shear. That means we are leaving a plane undistorted and unrotated. So if I now transform that into martensite, this is the shape it would become because I've sheared it on those vertical planes, right? It would change into a square shape. So this is the observed shape, but it's got to be the wrong crystal structure because you cannot change austenite into martensite by a shear, right? We've proved that the combination of Bain strain and rigid body rotation is an invariant line strain. Okay? You cannot actually leave a plane fully coherent. So although we have the correct shape here, this is what we observe, it's the wrong crystal structure. So there's something missing here. Okay? And I'm representing this shape deformation by this matrix P. Now, if I now shear it on this plane, okay, on the horizontal plane, then the combination of two shears leaves a single line unchanged, right? Because every line on this plane is unchanged by this shear, every line on this plane is unchanged by this shear. So if I have two shears, then there's only a single line left. So combination of two shears on different planes is an invariant line strain. Okay, so I'm going to do that. Here you are. If I shear on this plane, then I generate the right crystal structure because this to this is now an invariant line strain. But of course this is now the wrong shape because this is the correct shape. Okay? So the problem is not completely solved. I need to correct the shape to this without changing the crystal structure. Okay? So what kind of deformation can I use in order to change the shape without changing the crystal structure? Any ideas? What kind of deformation do I need to use in order to change the shape without changing the crystal structure? So you know when you deform a piece of steel, say interstitial free steel, it doesn't change its crystal structure, right? So what is the mechanism of deformation? Slip, yeah. So we can slip this crystal periodically so that its shape becomes this. Is there any other kind of deformation which doesn't change the crystal structure? Twinning, yeah. So we can have two different modes which will alter the shape but not change the crystal structure. Here is twinning. So I periodically twin this crystal, and you can see the macroscopic shape now is correct, and the crystal structure is also correct because twinning does not change the crystal structure. It just puts it in a different orientation. And inside this martensite, we should expect to see twin interfaces. And the second mechanism is slip. If I periodically slip this crystal, I can change its macroscopic shape into this without altering the crystal structure. Okay? And in this case, I do not get any interfaces inside the martensite, but I will see slip steps. Okay? So this is the complete solution because even if these planes are rational planes, okay, like 111 or 101, the average plane here is not. It's a combination of rational planes, and the average plane will be determined by how much slip or twinning I need to correct the shape. And that predicts the observed habit planes. Okay? Do you understand what I just said? That these facets here might be rational facets. Okay? But the average plane here can be anything depending on how much slip or twinning we add to the martensite. So everything is now explained, and furthermore, the prediction is made before the observations were done that sometimes martensite will have internal twins. Okay? And when electron microscopy became available, those twins were discovered. I'll show you a slide later on. So all of this is the complete theory of martensite, that to change from austenite to martensite, the deformation is a combination of the Bain strain and a rigid body rotation. the rigid body rotation converts the Bain orientation into the observed orientation and gives us one invariant line, which is the minimum requirement for martensitic transformation. But the shape here is wrong, because when we observe the macroscopic shape change, it's an invariant plane strain. And to achieve the correct shape, the crystal of martensite will periodically slip or twin, such that this average plane on which it's actually forming is not a rational plane, even though the individual facets here are rational planes. Okay? So this is what a martensite plate would look like. If it has slipped, of course we don't have any structure inside the plate. If it is twinned, then we will see twin interfaces inside the plate. And this is one of the early observations of twins inside a plate of martensite. Look at the scale here. So the spacing here is of the order of 200 angstroms, and the whole crystal is periodically twinned. This is actually the interface between the austenite and the martensite. And you can see the line features that I was talking about in the last lecture. Yeah? This is a transmission electron micrograph. The first observation was actually done on a replica, a carbon replica, because tin foils came later after the carbon replicas. But you need tin foils to prove that these are twins. Okay? Now, the next question is, when do we get twinning and when do we get slip? Any ideas? If I deform a piece of steel at a normal strain rate, then it will slip. Yeah? If I put an explosive and blast the steel, I will see lots of mechanical twins, right? So when martensite forms extremely rapidly, the interface is much more mobile when we have twinning. Okay? So martensite that forms extremely rapidly will be twinned, and martensite which has a dislocated interface and you produce the slip steps will tend to be slipped martensite. And if both of these processes happen perfectly, you will not find dislocations in the martensite. Okay? So, one of the things you could have mentioned when I asked you about the characteristics of martensite is a high dislocation density. What I'm saying here is that there should be a zero dislocation density in the martensite. Yeah? And that is why we get the shape memory effect. The interface reverses without producing defects. If it produces defects like dislocations, then the interface would become blocked and you lose your memory effect. And that's why eventually, when you reverse a memory element many, many times, it loses its memory because the defects interfere with the movement of the interface. So martensite which forms perfectly will not contain a high dislocation density. The dislocations that you see in ordinary steels are because the shape change relaxes by plasticity. So if I look at the shape deformation, so this is my surface, and the formation of martensite will cause the surface to tilt like that. Yeah? Invariant plane strain. But if you are forming martensite at a relatively high temperature where both the parent and product phases are mechanically weak, then this deformation is very large and it cannot be sustained elastically. So what happens is we get this tilting, but then we get plastic accommodation. This is alpha prime, gamma, and gamma. This is plastic accommodation in the austenite. So the austenite is not able to support that large shear. And that is what generates the dislocations, because then when the martensite plate becomes thicker, it absorbs those dislocations. So the dislocations that you see inside martensite are because of the plastic relaxation of the shape change. So dislocation density, the high dislocation density is due to plastic relaxation of shape change. And generally, when the MS temperature is high, MS is the martensite start temperature, the first temperature at which martensite forms during the cooling of the austenite. So it simply isn't true that martensite will have high dislocation density. Otherwise, we would never get shape memory effects. Now, there's one further point which I haven't addressed, which I identified in the difficulties, and that was that epsilon martensite formed exactly on 111 plane, right? It was not an irrational plane, and so forth. And epsilon is hexagonal close-packed. So if I look at the close-packed planes, then they are stacked in the sequence AB, 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 A. Yeah? And austenite is cubic close-packed, and the same planes are stacked in the sequence A, ABC, ABC, ABC. So it's very easy to see the deformation which would change austenite into epsilon. All I have to do is change this stacking sequence into this stacking sequence by shear on those close-packed planes. Yeah? So to change the stacking sequence, we need dislocations whose Burger's vectors are not lattice vectors. That means when you operate the dislocation, it will change the stacking sequence. Normal slip doesn't change the stacking sequence because the Burger's vector is the lattice vector. It moves from one position to another identical position. But what we want is a partial dislocation. So if I draw out that close-packed plane, close packing means the atoms touch each other. So these are supposed to be round. Okay, so that's a close packed plane. And a lattice vector goes from this position to this position, and that's an A by 2, 1, 1, 0 Burger's vector. Okay, so if I move from one point to the other according to that vector, there is no change in stacking sequence. However, if I move the layer on top from this position to this position, that is not a lattice vector. That is an A by 6, 2, 1, 2, 1, 1 vector. Okay? So that's called a partial dislocation. Partial dislocation, because it causes a change in the stacking sequence from A to B. And this is also a partial dislocation, and that is A by 6 into 1, 2, bar 1. If I add these two up, you get this vector. Okay? So what I've got to do is to pass one of these partial dislocations on every successive plane to change ABC, ABC into AB, AB. And that's exactly what happens during the formation of epsilon martensite. It's just like slip deformation, but the Burger's vector is not a lattice vector. Okay? So for the epsilon martensite, pass an A by 6 2, 1, 1 dislocation on every successive 1, 1, 1 gamma plane, and that changes the stacking sequence of gamma from ABC, ABC to AAB. Changes stacking sequence gamma, which is ABC into AB. Okay. Now this is just a shear, yeah? And a shear leaves the plane on which it occurs completely unchanged. So that's the habit plane of epsilon martensite. It's exactly the shape deformation that we see. So in the case of epsilon martensite, the diagram that I drew earlier is extremely simple. That I simply shear the austenite on these planes and I get the correct shape and the correct structure. And that is the reason why the habit plane of epsilon martensite is exactly 111 gamma. Now let me ask you a question. Is the density of epsilon martensite the same as that of austenite? They are both closed-back structures. Okay? So is the density identical? Do you know what the structure of the iron in the middle of the earth is? The solid iron? Hexagonal, yeah. Why? Yeah, high pressure. Yeah. Now, what does that imply? That if epsilon is stable at high pressure, what does that imply? Yeah. So epsilon iron has a higher density than austenite. That means that just a shear deformation cannot describe the transformation, because a shear doesn't produce a volume change. There must also be a small change in volume normal to the habit plane. And this is a beautiful experiment which was done in Birmingham University. When you look at a stacking fault in a transmission electron microscope, it looks like this because it's inclined to the thin foil, and these are just depth fringes. Okay? A stacking fault is like a thin layer of epsilon martensite. But you have to prove that, because it can only be epsilon martensite if there's also a volume change. Right? And this experiment proved that individual stacking faults also have a volume change. Now, supposing I look at this fault and I image it using G dot R equals 0. Are you familiar with that? Are you familiar with imaging Berger's vectors by using reciprocal lattice vectors which are at 90 degrees to the displacement? So there's a technique in electron microscopy where you can make a dislocation disappear if you use an imaging vector which is at 90 degrees to the displacement, because then the displacement is not visible. Right? Similarly, in a stacking fault, if you do an experiment where G dot R equals 0, then this should disappear. And look, in this slide, it has disappeared. The contrast has disappeared. It's as if the stacking fault is not there. But notice very carefully, it hasn't completely disappeared. And the reason why it hasn't completely disappeared is because of the volume change normal to the fault. So this is the first ever experiment which proves, first of all, that a single stacking fault can be regarded as epsilon martensite, a nucleus of epsilon martensite. So if you have a perfect dislocation which is A by 2, 1, 1, 0, and it dissociates into partials, then inside, in between the partials, you've created epsilon martensite. And in this paper, they also studied a sequence of alloys where the volume change should be different. Right? So if you change the concentration of cobalt, then the volume change on the gamma to epsilon transformation changes, and the contrast here changes. If the volume change is almost 0, the contrast disappears. As the volume change becomes bigger, the contrast becomes darker. So the real shape change when you get epsilon martensite is not simply a shear. So this is gamma. Okay. Then epsilon will lead to both a volume change and the shear. And the shear dimension is simply given by this vector divided by twice the spacing of the 1-on-1 planes. Okay? So we've solved the crystallography of alpha and epsilon martensite. You can predict every feature of those two transformations completely using the theory of crystallography. Is everyone okay with that? So let's now look into the thermodynamics of the martensite transformation. So incidentally, there's no other transformation in steels that I know of where you can predict things so accurately. Okay? Because martensite is a very simple transformation. There's no diffusion involved. Martensite plates never cross an austenite grain. Whereas, if you look at pearlite or electromorphic ferrite, it will grow across an austenite grain because it involves diffusion. So you've lost the connection with the original austenite in which it nucleated. But martensite only grows in the grains in which it's nucleated because it's a displacive transformation. Now, some of you might be familiar with this diagram, but others may not, so I'm going to explain it. This is the iron-carbon phase diagram, part of the iron-carbon phase diagram. This is ferrite, this is the A1 phase boundary, and this is austenite. And on this side we have completely austenitic material, on this side we have completely ferritic material. And the way in which we can calculate these phase boundaries is we plot the free energy curves of ferrite and austenite. So, if you have thermocalc or empty data and so on, you can obtain these free energy curves from that software. Yeah, are you familiar with that, roughly? Yeah. If I then draw a common tangent to these two curves, that gives me the equilibrium composition of austenite and of ferrite at a particular temperature T1 for which these free energy curves are calculated or measured. And the locus of these points as a function of temperature gives me the A1 phase boundary, and the locus of these points as a function of temperature gives me the A3 phase boundary. So that's just the equilibrium phase diagram for equilibrium between austenite and ferrite. What I want you to notice is something which is not plotted on the equilibrium phase diagram, and that is this point here, where austenite and ferrite of the same composition have the same free energy. Okay? If I plot the locus of that green point as a function of temperature, then I get another line which is called a T0 line. The importance of this line is that if I have austenite of composition greater than this dashed line, it cannot transform to ferrite without a composition change, because that would lead to an increase in free energy. But if I have austenite of composition less than this green point, then it can transform into ferrite without any composition change and a reduction in free energy. So diffusion-less transformation is impossible if the austenite composition lies beyond the T0 point. Okay? That's the important point. Martensite can only form at a temperature below the T0 boundary. Okay? So if I have austenite of this composition, it's possible for martensite to form. But if I have austenite of this composition, it's impossible for it to form, because that would lead to an increase in free energy. Okay. I will use this T0 curve frequently when we come to other transformations. So it's important to understand it, and it's very easy to calculate it, either using thermocalc empty data, or you can download free software from my website to allow you to do this as a function of the full chemical composition of your steel. So martensite can only form below, when the austenite composition lies below the T0 line. Okay? Now, in this diagram, we have nothing about strain energy. And we know that the martensitic transformation is dominated by strain energy, right? So we've got to allow for that strain energy. So martensite will not form as soon as the austenite reaches below the T0 curve. You have to allow for a greater undercooling, which corresponds to the strain energy, the interface energy, the twin interface energy. When you add all those terms up, you can define the undercooling, and therefore you can define the MS temperature. So just to show you the magnitudes involved. To allow for the strain energy, we can raise the free energy curve of ferrite. So this is ferrite plus the strain energy, and that will have the effect of shifting the T0 curve to a lower carbon concentration. And typically, the strain energy due to martensitic transformation is of the order of 600 joules per mole. If the martensite is twinned, then you've got to allow for the interfacial energy of the twins, which is of the order of 100 joules per mole. But the gamma alpha prime interfacial energy is really quite small when you have a macroscopic plate, because the surface to volume ratio is very small. And in general, the energy due to dislocations is much smaller in comparison. So if I add all these up, let's say it comes to something like 700 joules per mole in total. So I've got to cool below T0 until the free energy change between austenite and ferrite without any change in composition becomes 700 joules per mole. And that way I can calculate the MS temperature. So just to repeat that on a diagram, if I'm plotting temperature over here and the free energy change for transformation without any change in composition, okay, so this is the free energy change. Equal to G alpha minus G gamma, and no composition change. And this is 0. We go downwards, it's negative. Then it starts at the T0 temperature here, and is approximately linear. Okay? At T0, delta G is 0. Okay? Now, the stored energy of martensite, let's say it's 700 joules per mole. Add up all those terms. So when does this become minus 700 joules per mole? So if I do that, that gives me my martensite start temperature. So if I know the effect of manganese and gold and so on the free energies of alpha and gamma, then I can calculate the MS temperature. Yeah? All I need is the free energy curves of alpha and gamma as a function of composition. And all these software that I mentioned allows you to calculate the free energy as a function of composition. There are complications, yeah? So the MS temperature doesn't just depend on the chemical composition. If you reduce the size of the austenite grains, then the MS temperature decreases. If you deform the austenite before transforming to martensite, the MS temperature decreases, and so on. But all of these effects can actually be taken into account, and the MS temperature predicted both for alpha prime martensite and for epsilon martensite. And I don't know if you know Hong Suk Yang, but he put all these factors together, and there is some software which you can download from our website which will allow you to calculate MS using this simple method as a function of chemical composition, as a function of the austenite grain size, and as a function of the amount of deformation that you put into the austenite. Whether it's rolling deformation, wire drawing, forging, it doesn't matter what kind of deformation, it's possible to calculate the effect of that deformed austenite on the MS temperature. Okay? MS is the martensite start temperature. Okay. You need a little bit more than just the MS temperature. You need to know how the fraction of martensite changes as you go below the MS temperature. And there's a very famous equation called the Koistinen and Marburger equation. And Marburger, I think something like 1953, which works extremely well. So 1 minus the volume fraction of martensite is equal to exponential minus 0.011 into ms minus t. Okay? So this factor is almost identical for most steels. Okay? This is simply the temperature below the martensite start temperature, and this is the volume fraction of martensite. So that gives you a very good estimate of how much martensite you will get as a function of undercooling below ms. And there's no meaning actually to the mf temperature. That means the martensite finish temperature, because if you look at this equation, you will never get 100% martensite. But you can define your mf temperature as, say, that you've reached 95% martensite. Okay? For practical purposes, you can define such a thing. But fundamentally, there's no meaning to mf, and you will always have a tiny, tiny amount of retained austenite left between the martensite plates. So this was the athermal transformation that somebody talked about in the first lecture. Okay? So just imagine, in 2 lectures, you're able to know how to calculate the complete crystallography of martensite, and also the transformation temperature and development of transformation below the ms temperature. You cannot do that for any other transformation in steels. So the last paper that was written on this had the title, the complete theory for the martensite start temperature. That was Hong-Suk Yang's paper. After that, there is no more research needed on this subject. Okay? I'm joking, but there's an awful lot you can do by calculation now instead of making measurements of the martensite temperature. Now, in the next lectures, I'm going to talk about bainite, and it's much more confusing as a transformation because it's forming at temperatures where it's possible that you might have some diffusion happening during transformation, but we'll see. We will go into that in detail. And once we have dealt with the theory of bainite, we'll be able to design some really nice steel. So there will be a lecture on the design of bainitic steels, which actually has led to commercial success. Okay? Do you have any questions?